Today I want to talk about perspectives of quantum technology in classical networks, so to say, taking the perspective of a classical network engineer. Things work. Perfect. So the results that I show you are joint work with Stephen Diadamo and Matteo Rosati, and I would also like to acknowledge some funding here by the DFG, by the MCQST, and by the BMBF. To give a brief overview, I will first talk about entanglement as a coordination mechanism for communication networks. I will present a very small model, and then about the potential of using entanglement as an accelerator for data transmission, and finally about joint detection receivers. So to start with, entanglement as a method for coordinating parties. Here you all probably know this famous CHSH game where we have two aliens here that give bits X to Axel and Y to Bailey. Here. So these at the bottom here are two humans, and these humans are supposed to respond with 2 bits. Axel will respond with bit A and Bailey with bit B. And they win the game if this condition here is satisfied. And the classical winning probability is 0.75. This game is interesting if you put it into, let's say, a context of interstellar game, where these two humans are very far apart and they cannot communicate to each other, because then it allows you to speculate what the use of entanglement for networks could be. Because if you give them a shared entangled state, then they can increase their winning probability. And this works by them performing a unitary operation, which is conditioned on the input that they receive, here Ux for Axel and Vy for Bailey, and afterwards they measure in the computational basis and they respond with the measurement result to these aliens here, and thereby they increase their winning probability to 0.85. And so I thought maybe it would be interesting to study this for a communications context. So I developed a model. This is the scheme, and this shows this is kind of a supremacy result for quantum communication, because one can tweak this model in such a way that it works only if you have entanglement in it. So what is the model? You have here Alice, and here you have Bob, and they communicate to Charlie, and Charlie gets to see the modulo 2 sum of their bits. Then we have a channel here which modifies the signal that Charlie receives with x times y. X times y is just added. So this is how the CHSH game enters the model. Then we need to give partial information to Alice and Bob. So Alice gets x and Bob gets y. Actually, it's not really Alice and Bob that get this input, but some modulators, some technical device that they use to modulate their bit that they want to transmit. And then we take a fourth party into this game, James, who's trying to jam the communication. And James also knows what is the channel state. He does not really need to know x and y, but he needs to know the channel state. And he knows what these modulators do, but we put a power limit on James. So we allow James to change within 1,000 transmissions, maybe just 90 of the bits. So he can perform bit flips. And if we do that, we learn that in such a system, such a very hypothetical system, the communication is only possible if we give an additional plug-in resource here, the entanglement. Okay, so that's from a theoretical perspective, or information theoretical perspective, pretty nice. If you set this power limit correctly, which is described in this theorem how to do it, then you will prohibit every communication if the entanglement is not there. And this only works if you give the entanglement to Alice and Bob. yeah, there's also related work here by Leditsky, Alehi, Levin, and Smith in a different context where they study the impact of the entanglement, shared entanglement on the complexity. So what is the takeaway here? That looks pretty complicated, I would say, and also rather impractical. It's actually very hard to find such a system in practice. In practice, we have a very different machinery at work. So in the communication systems, we can look, for example, at the evolution of broadband connectivity, mobile connectivity, and we see that in the first generation of mobile networks, we had voice connectivity brought to the people, also in the second one. So here it was more for business than for end consumers. And then we had broadband internet, and now we have network-controlled robotics, tactile internet. All of this takes quite some time, and is a big industry behind it, which has sometimes a bit unfortunate metrics, at least from the perspective of fundamental research. It's all about cost reduction, about cost per bit. From my perspective, there's a lot of, say, incremental innovation, but it's done well so that things match, so that the number of small incremental add-ons, they add up to something bigger. For this, there's a lot of coordination necessary between the people. So for example, they coordinate by segmenting a network into these nice layers, where actually our quantum resources or quantum systems here are here at the very bottom. And yeah, then a huge effort is spent into standardization. A lot of work goes in there. And the problem that I encountered now is typically the following. Current technology tends to work well. It's not so easy to go to some technical system and point at it with a finger and say, here is where you have to put in your entanglement plugin. That's really hard. Okay, so let's for the time being, since I cannot point out exactly where's the point where one can make some positive change, which is somehow in line with all this industry, we can study a second example of a communication system, which is a bit, say, more practical. So here we have basically dense coding. I'm guessing you are all familiar with dense coding. Here we have Axel and Bailey, and again, they get access to shared entanglement. And they transmit here over a noisy channel. So here's a noise source, and they have some loss. And it has been found early on, or observed by Bennett and co-authors, that for such an entanglement-assisted data transmission system, we can have possibly infinite gains in terms of capacity. So many bits per second more than we could send without the entanglement. That's, of course, nice. That's somehow in line with network evolution. And then we have here recent results by Guha, Zhuang, and Bash, who investigated this phenomenon from a bit more like practical approach and suggested how one could actually build such an entanglement-assisted communication system. And they also pointed out that for like standard communication system where you use, for example, two-mode squeeze and vacuum as the entanglement, you will get such a behavior here that the entanglement-assisted capacity divided by the non-assisted capacity scales logarithmically in 1 over the photon number per pulse. That already tells you, okay, if I have very small photon numbers, then some magic happens. That's going to be very nice. So before I come to the contra side, let me point out how we investigated this, let's say, from the network side. So here we have these layers. I already told you or depicted them. And then we can think of a quantum-aided system where we only change the lowest layer here. And in this layer, we use kind of dense coding, or entanglement-assisted data transmission. So we studied this as a queuing model, very nice theoretical work. Then there was also follow-up work in a similar direction, but which studied more, like, say, also complicated technical aspects of Perek, Boch, and Deppe. And we saw, okay, so if you use the entanglement-assisted data transmission, you can reduce the number of bits that get dropped at the sender-side buffer of such a system, and you can, of course, increase your data throughput. But there are some drawbacks as well. So the cost per bit is probably not going to decrease because it's very complex. Also, we have troubles with the storage times. So I guess yeah, some of you have already discussed it with me, how one could, or what are the prospects, how can we increase storage times, what can we expect. And what we have done in my group is also to investigate to some degree the use cases. Because if you have such a communication system that generates entanglement while it does nothing else, while there's no data to transmit, and use it as a booster when the data arrives at the sender side, then you can accelerate only certain types of data transmission. You cannot send continuous data streams over this channel because then you get no benefit from the entanglement. It only helps you if you have sporadic, very high data peaks. And then the next question is, what's the application for that? Who has such a system? Who wants to have that? So this is something we also investigate. Yeah, given these drawbacks and given the fact that we also focus to some degree on a 10 years horizon, the next thing we studied is the Holevo capacity. Just let go of the entanglement in the network and think of putting a quantum computer into your receiver. That's kind of the idea. And then let's quickly compare this to the current status on a very high level. So currently a communication system where you have, again, Axel and Bailey, but this time no shared entanglement, operates like this. So Axel sends, say, some pulses, some laser pulses. Here, on the right-hand side, you see them, to Bailey. And Bailey has a detector here. And whenever a laser pulse enters the detector tries to figure out what type of pulse was that. So here we study something which is called BPSK, binary phase shift keying, where each pulse is either a plus or minus. And we assume everything is detected correctly. So eventually Bailey will know this sequence here that Axel tried to send. In comparison to that, a joint detection receiver, or like what is basically the content of Holevo's work, works totally different. That's the kind of quantum computer as the receiver. Yeah? So this thing will just wait until all pulses are in the receiver and then do some quantum magic. Again, the question arises, what's it good for? And now I want to quickly study some actually numbers mostly. It's really about numbers and about trends. So here we see the difference between the conventional system and this optimal joint detection receiver. Yeah? This is what the quantum computer as a receiver. So and how is this to be understood? So here we assume that we transmit a constant number of photons per second, but we modulate faster and faster and faster and faster. So the number of photons per pulse goes down because the duration of the pulses shrinks. Then we can just go do some very simple equations, and we see, okay, so this capacity of the Holevo system scales with the logarithm of the baud rate. So that's the B here is the baud rate, and you see the baud rate depicted below here, and yeah, that's the difference. I like it a lot because it's kind of this thinking of looking at classical computing where you have Moore's law coming to an end. Turning the old knobs doesn't work so well anymore, so you resort to using some quantum mechanisms, and this is depicted here in a nutshell. That's why I like it a lot. So this is what happens if you increase the baud rate for using the conventional strategies, and the top curve is what happens if you use the best known quantum techniques in comparison. And that, as you can see here, can be cast into a very practical scenario. So I can go through the numbers, say, okay, let's give this a loss of a 185 kilometer link. Let's put 1 milliwatt laser source. Let's study the C-band of the current transmission systems. Okay. The question is now, of course, is it practically relevant? I cannot give you the answer yet. I can just show you some numbers. So here are the formulas for those who are interested. This is how to compute these capacities. You see here that the Shannon capacity is a logarithm of basically the signal to noise ratio. So this here is the noise, and this is the signal. This is very well known in the communications engineering. You want to optimize your signal to noise ratio. It turns out that if you want to optimize the Holevo quantity, this is not the truth anymore. If you optimize the signal to noise ratio, it's not necessarily optimal. Okay, what can you do with it? For example, you can study your current transmission system where you have multiple amplifiers on an optical fiber, and you can check what happens if you replace the receiver with a joint detection receiver. Then you see for short ranges with few amplifiers, here, this is this region here, you can actually tune down the amplifiers and save some energy. We were pretty excited about this. There's previous work here by Yarzynia and co-authors, and I worked on this with Matteo Rosati. But then you talk to this about this with, like, say, practical communication system designers, and they tell you, oh, yeah, but you know, that's not really our problem. Our problem is the receiver, not the amplifier. Amplifiers, actually, okay, we knew that they don't consume so much of the energy, but I mean, you have to start somewhere. So maybe next year we talk about receiver design. Okay, now for the last minutes, we can study some numbers again here. So the baud rates today are something like 200 gigabaud in research. So these are like record-breaking systems. They call it hero experiments. Whereas the commercial systems that we all use every day, they are at 80. And if we think of the current system design, then the standard, the established standard, is to have one amplifier every 80 kilometers. Maybe sometimes it's 60, sometimes it's 100, but the rule of thumb, 80. And if we take such a system here, then put in the loss here of the fiber and study the laser source in a, let's say, roughly reasonable regime. I'm not myself an optical communication system engineer, but I read in the literature. Then we can theoretically achieve this pretty insane number here in terms of bits per second. And we can expect a factor of 4 in the capacity when we use the joint detection receiver if we go to this baud rate, 10 to the 18. That's, of course, quite a lot. So maybe this is not what we want to look at if we think of using quantum technology for commercial optical systems. So we take some other number, maybe 220 kilometers, and let's say we want to save the amplifiers. We want to have unamplified fiber over 220 kilometers. We can again calculate the loss. We put a slightly weaker laser. Then we get something a little bit below a terabit today in terms of bits per second, and we can expect a factor 10 gain if we go slightly above 10 to the 15 bauds. Okay, that's still a bit much, I guess, given the current status. So how does this look like from, let's say, higher level? In what region are we trying to navigate here? Well, we have here on the one hand side photons per second. That's our transmitter, the power that we have at our disposal. And on the x-axis here is the baud rate. These are the two quantities I tweaked here. And the current status is that we have to somehow live in this region here with our design. And the question is, because in this region, I told you the differences are not so large between the two systems. The question is, to some degree, what are the systems where the difference gets larger? So already here you can see, this is the Holevo side of things, the joint detection receiver. You see here this slight angle in the curves that tells you this thing is sensitive to baud rates, whereas this thing here is pretty much flat. It does not react at all. So it's a new design option, I would say, but it's pretty hard to tell where to use it. Okay, here we can see again, where we can expect certain gains in our 220 kilometer scenario. And you see the factor 10 gain is pretty far out if we look at the status today. Why is it interesting nonetheless? Because it's a trend. Like Moore's law, this is a trend. This is the trend of baud rates over years. I finally found a good source for this here, this very nice summary. And it tells you that baud rates are going up. So if we want to project this to 10 years in the future, then we would say something like, okay, in 2030, maybe we are at 300. And then if we again look at our 220 kilometers link, and again take 1 milliwatt laser here, then we see, we will get a factor of 2.3 in 10 years from now, if we use quantum technology. Or maybe we should say the other way around. If we don't start thinking about the quantum technology, we will lose out by 50%. Okay, and last but not least, I should say something that is always important: is it commercially interesting? If you get a gain in a situation which is not interesting for anybody, then it's irrelevant how large your difference is, your gap. Okay. There are practical designs possible for this. Joint detection receiver has there has been some method invented by Zakat Guha and invented by follow-up works by other authors. Rosati, Klimek have also shown some different possibilities here. Something that I find very interesting is the new optical fiber types. So we don't necessarily have to stick to our single-mode telecom fiber for all the future. I talked only about optical fiber links in a network, but the future looks a lot more complicated. Already now we have also wireless, and in the future we will also have satellite links, which bring their own characteristics, which I did not talk about here. And in order to narrow down things, we have invented a workshop, which is going to be held in Taiwan in 2023. That's the third version of the workshop already. Is not only focused on this topic. Okay, thanks for your attention.
Do we have questions? Okay, so actually I have...
Bulat has a question.
Okay.
Very nice talk, Janis. And can you flip back to the previous slide? We had a graph of the from the roadmap with the bars. Yeah. So one can clearly see from this graph that the advance was actually not in getting a bigger constellation, but making the symbols repeat themselves more often. You can see that the top at 192 gigabaud is just your very, very common QPSK. And there's multiple reasons for this. We discussed them with Dan Kilper at last TACN. how have you looked at the Holevo bound for QPSK modulation and whether it actually increases in this? Is there a commercially interesting regime for this?
Yeah, thanks for the question. The answer is no. I think there's many possibilities to narrow down to understand better whether it's a 2.3 or whether it's a 23 or 0.23, the gain that we can expect here at some point. One reason is that, as you say, these are not idealistic information theoretic models that produce these numbers, but actually concrete constellation diagrams, concrete designs, which are sometimes far from optimal. Although I would guess that these ones here are pretty close. The second thing is that it's not only the code book that we think of is hilariously idealized, but also the channel model is of course wrong. In this commercial regime, we know that we have many different effects like Kerr nonlinearity or cross-phase modulation, which are not really in this model here. Yeah.
Okay, I also have a quick question. How long would it take until we have this quantum joint detector on the table?
Oh, you have to take a look at Bulat. He's looked at it if he wanted to cry.
20 years.
20 years, yes. Okay. So, Bulat said 20 years. I'm, of course, hoping for a lot less.
Okay, if there are no more questions, let's thank our speaker again.
Oh, thanks.
Thanks very much.